All right, today we are going to look at lesson 11.1 and 11.2, which deals with the definite integral and also the fundamental theorem of calculus. There's two main branches of calc, differential calculus and integral calculus. Now, we've spent the majority of our semester focusing on differential calculus, and that's where we learned about limits and tangent lines and their connection to derivatives. In Unit 10 and Unit 11, we're going to begin to look at the other branch of calculus, which is known as integral calculus. Now, what's important to note is the definite integral arises from the solution to the area problem. Now, we didn't go into too much detail with the area problem because we kind of ran out of time. But what's really important for you guys to know is that the area problem is to definite integrals as the tangent and rate of change is to derivatives. So if you remember our unit 1, we kind of focus on tangents and slopes and rates of change and instantaneous velocities, and they all kind of came back to this one big idea of derivatives. Now, the same is true when you look at the relationship between the area problem and the definite integral. Now, just like before, all derivatives weren't slopes. All definite integrals aren't going to be areas, okay? But this is where it originates from. So in this box here, it says, let f be a continuous function over a closed interval a to b. Then the definite integral from a to b of f is written with this, it looks like this kind of big elongated s, and it's actually called an integral sign. And it says basically exactly what we just stated above. It's the definite integral of f of x from a to b. Now let's just kind of go through the notation. This symbol was introduced by Leibniz, and it's called an integral sign. The notation, the integral of a to b of f of x dx, f of x is called the integrand. Okay, so this is the integrand. A to b are the limits of my integration, or the bound that we're going to look at. We're going to be kind of closed between two bounds, and that's going to be a definite integral. And if we look specifically at a, that's our lower limit. And if we look at b, that's our upper limit. So we basically start at a, go to b, and we're looking at, the integrand of f of x. So the procedure for calculating an integral is called integration. Now, a special case where our function is greater than or equivalent to 0, we're specifically looking at the area under a curve or the area of a graph, and it could be between two graphs, under a curve in the x-axis. But basically, if f of x is greater than or equal to 0, we can also say that this is an area along with just being an integral. Okay? But like I said before, an integral does not need to represent an area. Okay? So from section 10.1, we talked about f of b minus f of a being our area, okay, where f was any derivative of f. So, where big F is any interderivative of little f. Okay, therefore, we can then say that this integration that we just talked about above is therefore equivalent to f of b minus f of a, because they both represent an area. This represents an area, and we talked about this being an area as well. So there's two different ways to look at it. One as an integral, and one as just two antiderivatives where you're subtracting the lower bound from the upper bound. Okay, and then this little statement basically says if you take the derivative of the antiderivative, you end up with the original function itself. And this lends itself nicely to what we can say as the fundamental theorem of calculus. Okay, so it says if f is continuous on the interval a to b, then the integral from a to b of f of x dx is equivalent to f of b minus f of a, or this way of representing the area is equivalent, again, to the area, just written in a different notation. So when we first do our first example, we will use it, where we'll look at it from the perspective of 10.1, and then we'll move into this new notation. Basically, what's happening is we can integrate. And when we integrate, we're dealing with the antiderivative, which is why we focus so much time on learning derivatives. Now, this integral, if f of x is greater than or equal to 0, can also represent an area between curves or an area under a curve. Okay, so let's kind of see what this looks like. Okay, so example 1 says, evaluate the integral from 0 to 5 of 3x minus x squared dx. Okay, so the first thing I'm going to do is I'm going to do it from our understanding of 10.1. Okay, and we're going to do one like this and check your understanding, and then we'll kind of put them together. So this right here, okay, we have the integral from 0 to 5 of 3x minus x squared dx. Okay, now the first thing I know is that this is equivalent to f of 5 minus my lower limit, f of 0. But I need to know what f of is. F represents an antiderivative. So I need to know my antiderivative of my function. So really, I'm looking at, I'll just write down here, f of x is going to be equivalent to 3. Then we add 1 to the exponent of 1, which is 2, x squared minus 1 all over 3 x cubed. And then we used to put this plus c on, right? This c was, there could be any constant. But what's happening is because we have a definite integral, meaning that you are bounded, you have a lower limit and you have an upper limit, we actually don't need this c here when we evaluate at 5 and at 0. Okay, so I'm going to eliminate that when I actually go and write out my entire area. So I'm looking at, now I'm focused on this piece right here. I'm going to plug in my 5 into my antiderivative. So I'm looking at 3 all over 2, 5 squared, minus 1/3, 5 cubed. Again, I'm ignoring that c because I have a definite integral now. And then here, I'm going to subtract from it. And here I have 3 all over 2 times 0 squared minus 1/3 times 0 cubed. Now, some of you are just saying, that's just 0. Yep, if you saw that, you could have just written that right away. This ends up being, this is 25 times 3. That's going to be 75 all over 2 minus, that's going to be 125 all over 3. And that's going to give us a negative 25 all over a 6. Okay, so we're just talking about our notation here. Now, really quickly, we can see that this actually cannot be an area, right? Like, even though I've set it up using my understanding of area, I'm actually just looking at the definite integral because you can't have a negative area. It doesn't actually make sense. Okay, so if f of x isn't positive, then your integral is just, it's the integral, right? Just like when you take a derivative, sometimes it's just a derivative. We don't always call it a slope until we need to. Okay, so what I would like you to do is I would like you to do the same process. Okay, I know I'm basically rewriting this integral using our understanding from 10.1, and then we're going to look at a new notation. Okay, so go ahead and work on yours. First, find the antiderivative, plug your upper bound in and subtract from that your lower bound, and you should end up with an area. If it's not positive, it can't be an area. It's just straight an integral. Okay, so pause your video. Here comes your solution. Okay, take a look at that. Again, if you have questions, let me know. Okay, so now there's different notation. So you very rarely see an integral kind of set up like this. Okay, we have a better way of doing it. So this right here is equivalent. There's two ways to write this. You can say that f of b minus f of a, which is the area under a curve, can be written as f of x, the antiderivative, and then you can write it as, it's kind of like like an end of a bracket, and then you say b to a, where b is your upper limit and a is your lower limit. Or it could be rewritten as f of x. Again, f is your antiderivative with a straight line b to a. Okay, there should not be a beginning to the bracket if you choose to write it in the what looks like kind of an end bracket. And what this actually allows us to do is rewrite this idea. So we won't actually be seeing this piece anymore like we did above. So I'm basically going to do the above problem, just written in a little bit different notation. So here, we're going to start with 2 negative 1 of x cubed dx. Okay, now what this is allowing us to do is basically, okay, write the antiderivative. So if I write the antiderivative of x cubed, I end up with 1/4 x to the 4th, right? Which is what you did right here. Okay, But what I'm going to do now is I'm going to put into place my new notation where I usually just use a straight line, and I put my upper limit 2 and I put my lower limit -1. It eliminates this side step here where you're trying to write, oh, this is my antiderivative, and then I'm going to go plug it in here, where you can kind of do all of that in one nice step. And then your next step is saying, okay, well, I'm evaluating this as 1/4, and then I put my upper limit 2 to the 4th, and I subtract from that my lower limit, which is -1 to the 4th. So here, again, you're looking at 16 all over 4, which is just 4, and that's here is going to be a -1/4, and you still end up with the exact same answer as you did right here. The difference is the way we kind of initially set it up. Now, when you're looking at derivatives, when you're looking at integrals, this is how you will see it written. Okay, we often don't see it like this. This is just a connection piece from the area problem in 10.1. Okay, so when you're dealing with a fundamental theorem of calculus, you're saying the integral from a to b of f of x dx is really f of x from a to b. Okay, and that's how we always write it. Okay, so now we're going to use this new notation, and we're going to go ahead and work through a few problems. Okay, so it says find the integral from pi to 2 pi of sine of x dx. So when I'm doing this, the first thing I do is I usually just write down what was given. So 2 pi to pi sine of x dx. And I say, well, this is equivalent to, and I say, well, what is my antiderivative of sine of x? Or what originally gave me sine of x? Well, cos of x gives me negative sine of x. So negative cos of x gives me my sine of x. And then I want to evaluate this from pi to 2 pi. Now from here, I just go ahead and I'm still doing f of b minus f of a, but I'm just writing it differently. So now I have negative cos of 2 pi minus a negative cos, so this turns into a positive cos of pi. And I know at 2 pi, my value of cosine is just a 1, but don't forget that negative there, so that's really a -1 now, plus cos at pi, which is also -1. So again, my integral is going to be a -2. Okay, so that's all there is for that one. And then we were going to do one more before you have some check your understandings, but I just kind of want to highlight a table of indefinite integrals. Okay, so what you're looking at, before I go down there, is when you're looking at this integration right here, I'm just highlighting it. This is a definite integral, and it's definite because you have a lower limit and you have an upper limit. Now, when you don't have limits and you're just looking at the integration, it's called an indefinite integral. Okay, so if you're looking at this table, this is a list of indefinite integrals, and really they're antiderivatives. Notice that if you're dealing with an indefinite integral, and which is right here, you have no bounds. There's no upper bound, there's no lower bound, which means you always are going to see that c because you have nothing to plug in. Okay, so if you don't have bounds, you need to make sure that when you write that antiderivative, you're dealing with that plus c or that plus any constant. Okay, when you're dealing with a definite integral, you have something to evaluate at, so you don't need that plus c. Also, when we're looking, there's a few of these that are on your formula sheet that you wouldn't need to memorize. Okay, so secant tan x tan x dx is really your secant, which again, if you remember secant of x, we had the derivative given to us on our formula sheet. Likewise, the integral of secant squared of x dx is also given, and the integral of cosecant x times cotangent of x dx is also going to be given to us on our formula sheet. Okay, so there's also kind of these rules where if we are taking a limit, you could put the constant on the outside of the limit and just kind of move down and acted as a multiplier. You can do the same thing here, and these are some properties of integrals. So if you have some constant being multiplied by your function, you can simply move that constant on the outside and just focus your attention on the derivative of f of x inside. Likewise, if you're dealing with, let's say, the addition of two functions on the inside, and again, you have a definite integral, you can break it up and look at the integral of f of x, and then you can add that to the integral of g of x, both evaluated from a to b. So that's what we're going to do, and I'm going to do this two separate ways because right now our understanding is pretty new, and I want to show you what happens when you break it up using our properties of integrals, but you don't actually always have to do this, and we actually kind of rarely do until we get into more complicated functions. So I'm going to do it two different ways. So the first way is breaking it up using this understanding. Okay, so I have the integral of 6x squared plus cosecant squared of x, and this is evaluated at d of x. Now, this is an indefinite integral. How do I know? There's absolutely no bounds on my integral. So I'm just looking at just any antiderivative here, so I'm going to include that c. So I'm going to break this up using these two properties. Now, the first thing I'm going to do is break it up into two summations because there's two functions, technically 6x squared and cosecant x, cosecant squared x. So I'm looking at 6x squared dx plus the integral of cosecant squared x dx. Well, this right here is a constant, so technically I can move that to the outside, and I have 6 with the integral of x squared dx plus the integral of cosecant squared x dx. So now what I can do is I can take the integral of each of my functions separately. So I will look at this one, and then I'll look at this one. So here I end up with 6 times 1 all over 3 x cubed. And again, technically I have this plus c here. Okay, so I have plus c. And then over here I have plus my antiderivative of cosecant squared, which you can kind of go up here and just say, oh, that's right here. That is negative cotangent of x. So I have plus a negative cotangent of x. And again, we have that technically that plus c. Well, if we kind of simplify things, a 6 times a 1/3, that's going to be 2x cubed minus cotangent of x. But when you add some constant to another constant, okay, you get 2 times that constant, right? But they didn't have to be the same constant, okay? So they could have been any constant. So you can still just say it's some constant. So I'm just saying plus a constant, right? If you add two constants together, what do you get in return? You just get another constant. So you don't have to write 2c, you don't have to write anything fancy, it's just plus a c at the end. Okay, so we end up with 2x cubed minus cotangent of x plus c is the integral, or the indefinite integral, I should say, of 6x squared plus cosecant squared of x. But like I said, I wouldn't really break it up like that. So you're fully able to do the following. So you're saying, okay, this is the integral of 6x squared plus cosecant squared of x dx. So when I'm looking at this, I'm going to look at the integration of each, but I'm going to do it within the same integral, okay? Or basically write it as my antiderivative. So here's my 6. I have 2 plus 1 is 3, x cubed. I know the antiderivative cosecant squared of x is negative cotangent of x. And then again, I just have 1 plus c. Or I have 2x cubed minus cotangent of x plus c. Again, I'm getting the exact same thing that I did, but in just a few less steps. This is what I did in blue here is why what's happening in black is allowed, but you don't have to show every single step. You don't have to pull the constant to the front. You don't have to break it up into two integrals. You're perfectly capable of just saying, hey, I know what's happening technically using understanding my properties of integrals, but I'm just going to kind of take the shortcut and just look at them all at the same time. Okay, if you're more comfortable doing it like this, well, the one I did in blue, then that's perfectly fine. I'm never going to take marks off for that. But you're also fully allowed to do it like this, and you would get full credit as well. Okay? All right, so you have two check your understandings to do. They're both dealing with the indefinite integral, so you always want to make sure there's a c attached at the end. And yeah, pause me. Go ahead and take a look. Work on both of them, and when you're ready, unpause and check your work. Here they come. Okay. Let me just scroll over. I did part B in 2 ways just to show you could pull out the 2. For part A, I rewrote them as 2 separate integrals. You didn't have to. You could have looked at this all at the same time, all at once. No big deal. Again, please make sure when you have an indefinite integral, you have no lower and upper bound. There is a c attached at the end. All right, so now let's look at some examples when we're dealing with the definite integral. Okay, so we're going to be bounded. Okay, so from here, I should make a note. This is going to be a definite integrals. Definite integrals. Okay, so the first thing I'm going to do is I am going to think about my antiderivative, and I'm going to write it using my understanding of the notation given by the fundamental theorem of calculus. So here I have 2 all over 4 x to the 4th minus 3 all over 3 x cubed plus 7 all over 2 x squared plus 2 all over 1x. And then right here, I'm going to say, well, I know this is being evaluated from 2 to 5. Now, before I plug all those values in, I'm going to simplify what I have written. And I have a 1/2 x to the 4th minus x cubed plus 7 all over, oops, if I can write a 2 correctly, 7 all over 2 x squared plus 2, and this is evaluated from 2 to 5. Now once I'm there, I can plug in my x value is a 5 and subtract from it when my x is a 2. So this right here, I'm just going to move over so I give myself enough room. We have 1/2. This is going to be 5 to the 4th minus 5 cubed plus 7 all over 2, 5 squared plus 2. And from that, we're going to subtract what happens when my x is a 2. So I end up here with a 1/2, 2 to the 4th minus 2 cubed plus 7 all over 2 times 2 squared plus 2, and then we'll close that bracket off. So now I'll get my trusty dandy calculator out, and I'll do my left-hand side, and then I'll subtract it from my right-hand side. If I plug in my entire left-hand piece that's in red, I end up here with 285. And if I plug the whole piece in that's blue, I end up with an 18. If we subtract these, we end up here with 267. Okay, so my evaluated integral here has a value of 267. Okay, so let's look at our next one. So here we are looking at the integral from 1 to 8 of 1 all over the cube root of x squared. Now, just like any other time we are dealing with a derivative or whatever it may be, sometimes it's easier to simplify things before you actually integrate. So when I'm looking, I'm going to leave this as 8 over 1, but I'm really looking at this is 1 all over x to the 2/3 dx. But I'm going to rewrite this again as the integral from 1 to 8, and this is really x to the negative 2/3 of d of x. Okay, once these get more complicated, which we'll see in the next lesson, we're going to learn things like substitution and integration by parts, and there's partial fractions, and there's a lot of different pieces that you'll learn in university. Right now, we're kind of sticking to some pretty basic integrals, so you can right now rewrite them into something nice and make them easier to integrate. Tomorrow we'll learn the first process, and then next year in the fall when you go to university and you take your first university calc class, you'll learn all these other processes that will help you integrate more complicated derivatives or complicated integrals. Okay, so here I'm saying, well, if I'm looking at my function, x raised to the negative 2/3, I'm saying, okay, well, technically there's going to be a 1 here, and then I have all over, if you add a 1 to negative 2/3, you end up with a 1/3 x to the 1/3, and again, this will be evaluated from 8 to 1. Or if I kind of simplify, that's going to be 3x to the 1/3, and again, we're evaluating from 1 to 8. If I plug these values in, I'm really looking at 3 times, this is really technically the cube root of 8, minus 3 times 1 to the 1/3, or the cube root of 1. That gives me a 3 times a 2 minus a 3 times a 1. That's a 6 minus a 3. That has a value of 3. Okay. All right, again, one more here before you guys have some to try. When we're looking at this one, again, I'm going to simplify it a little bit. I don't know why this says A. This should say C. That's going to be part C. I'm going to simplify this before I even attempt to take the integral. So here we're looking at an integral evaluated from 1 to 4. This is really t squared all over t plus t to the 1/2 all over t minus 2 all over t. And this needs to be in brackets so we know that it's all taken to dt. And now, again, simplifying a little bit more, this is from 4 to 1. T squared divided by t is really just t to the first, because t squared minus t to the first is t to the 2 minus 1. Plus, again, we have t to the 1/2 minus t to the first is t to the negative 1/2. And this is really negative 2 times 1 over t. Now remember, if you see that 1 over t, or 1 over x, you want to be thinking of the antiderivative as the ln of the absolute value of that variable. Okay, so now that I'm simplified, I'm going to go ahead and take my antiderivative. This ends up being 1 all over 2 times t plus 1 all over negative 1/2 plus 1 is 1/2. So it's 1 divided by 1/2 t to the 1/2 minus 2 times the natural log of t. Okay, and this whole thing, okay, I'll use the bracket notation this time. You don't have to. Is going to be evaluated from 1 to 4. Simplifying this, I end up here with a 1/2 t plus 2 times t to the 1/2, or the square root of t if you wanted to write it that way, minus 2 times ln of the absolute value of t. And again, we're evaluating from 4 to 1. Plugging all of this in, I put the value of t as 4 first, because I'm always going to subtract the lower limit from the upper limit. So we have 1/2 times 4 plus 2 times 4 to the 1/2, or the square root of 4, minus 2 ln. Now, I'm going to write this as the absolute value of 4, but I don't have to. I'm going to rewrite the next line as just a 4, because the absolute value of 4 is just a 4. You have to leave the absolute value when there's a variable involved, because you don't know what that variable is. And then here we're going to subtract that from when I plug a 1 in as t, so it's going to be 1/2 times 1 plus 2 times 1 to the 1/2 minus 2 ln of the absolute value of 1. Again, we'll talk about what that is, but I don't technically have to have the absolute value there because I know the absolute value of 1 is just a 1. Okay, so now if I evaluate, here I have 1/2 times 4 is going to be a 2. Actually, we'll just do this whole thing on this. No, I'll write one more line. So this right here is going to be a, oh, hold on a second. Sorry about this. When I did this piece, sorry, I knew something looked wrong. This is going to be 1/2 t squared, because when I do the 1 divided by 2, that's going to be t squared. 1 over 2 t squared, which means this should be a squared. Sorry about that. I knew something looked funny. Okay, so this is going to be 16 all over 2. That's going to be an 8. This is going to be 2 times 2 is a 4, minus 2 ln. I'm just going to write it as a 4. And then in green here, I have that minus sign. I'm just going to leave it in brackets for now. I have a 1/2 plus a 2. And then the natural log of 1 is just 0. So 2 times 0 is just 0. So I end up with a 12 minus 2 ln of 4 minus 2.5, or I end up with an evaluated answer of 9.5 minus 2 ln of 4. Okay? So there we go. Those are 3 definite integrals and how we evaluate them. Sorry about the confusion here. Hopefully I didn't lose any of you when I kind of went through that 2 back end. Basically, when I did t, if I want to take the integral, it's going to be 1 all over 1 plus 1 is 2, and then you have to do t to the 1 plus 1 is 2. I just missed that part. Sorry about that. Okay, so you guys have, I believe, 3 to do. so go ahead and do yours, and I'm going to kind of show you one more thing after putting things together in terms of the area between curves, which is technically lesson 10.2, but I kind of just want to show a little bit of a relationship so you understand where it's coming from. Okay, so go ahead, pause me. When you're ready, restart me. Here come your answers. Okay, again, notice with definite integrals, you should not have C's anywhere because you're evaluating them. Okay, here are your first two. You did not have to factor out the 5. I just did in part B. And then here is part C. Okay, again, technically, I don't need this. I should have changed that. I don't need that absolute value. It's 2 plus ln of 4. Okay, you do not need that absolute value there. Okay, all right, so find the exact area between y equals x to the 4th minus 2x squared and y equals 2x squared. Okay, so technically speaking, this would have been, I believe, 10.2, which is what we would have done if we had more time, but I want to show you the relationship. So what's happening is when you're doing and evaluating all these integrals, you're finding the area under the curve or the area between two curves, as long as the f of x turns out to be a function that's going to be greater than or equal to 0. Because if it's not, you end up with a negative area, which doesn't make sense. Okay, so for example, let me just kind of draw this picture here. Okay, so here is my coordinate plane. Y equals x squared. I'll draw it in purple. Looks something like, this, except let me actually connect it to the origin there. Okay, so that one is this one. And if I were to draw x to the 4th minus 2x squared, it's going to look something like this. Okay, nothing perfect here, not trying to be perfect, just trying to give you a sense of what's happening. Okay, so we're looking at these two. And we're purposely looking at the area between these curves. Now notice that the first one that I drew, which I highlighted in yellow, which is y equals 2x squared, is above, what happened there? Is going to be above my function x to the 4th minus 2x squared. Okay, so this is above, and then this one's going to be below. So I'm going to highlight this one. So this one's below. Okay, and we're looking for the area in between these. So I'm looking for this area here. Okay, just the area between those curves. Well, if I'm thinking about what's happening, I need to know what these intersection points are, because your intersection points give you your lower and upper bound. So if I want the intersection points between these two functions, I'm really saying, well, x to the 4th minus 2x squared has to be equivalent to 2x squared, right? I'm finding the intersection point so I can equate them. Well, if I move them over, if I move that 2x squared over, I'm looking at x to the 4th minus 4x squared is equivalent to 0. Well, here I can factor out an x squared. I'm looking at an x squared minus 4 equal to a 0. Here I have an x squared. This is going to be an x minus 2 and an x plus 2 equal to 0. Or I have three intercepts, x equals 0, x equals 2, and x equals negative 2. Now, because at x equals 2, this function is just continuous, and y equals 2x squared stays above y equals x to the 4th minus 2x squared, my intersection points that I'm going to be looking at for my bounds are going to be negative 2 to 2, because that's where I start and end, right? I'm going to go from negative 2 continuously all the 2. Nothing happens at x equals 2 where there's any overlap or anything. So I'm just looking at negative 2 to 2. So when I actually set up my integral, I'm looking at an integral from negative 2 to 2. And the function that I'm actually looking at is when I subtract x to the 4th minus 2x squared from 2x squared, because I want to subtract my graph that's below from the graph that's above to keep it positive. So here I have, again, I have 2x squared, and I'm going to subtract from that the function that's below minus x to the 4th minus 2x squared, and this whole thing is times dx. So if I kind of simplify that, I'm looking at the area, or the integral from negative 2 to 2, which is the area of 2x squared minus x to the 4th plus 2x squared dx, or the integral from 2 to negative 2 And I have, that's going to be a 4x squared minus x to the fourth dx. So now if you're looking, this is just what we've been doing the whole day. Okay, but it can come from a process about finding the area between two graphs or between two curves, right? And now we're just going to go through our process that we've done throughout today's lesson. And I'm going to say, well, I'm going to look at the antiderivative, which is going to be 4/3 x cubed minus 1 over 5 x to the fifth. And we're going to be looking at this evaluated from -2 to 2. Well, if I plug in everything we have here, I end up with 4/3 2 cubed minus 1/5 2 to the fifth minus, then in brackets here, I have 4/3 -2 cubed minus 1/5 -2 to the fifth. Okay, again, you shouldn't see any plus c's anywhere because we're looking at a definite integral because we're bounded. We're actually between two curves here. And if I evaluate this is going to be 8. That's going to be 32. Actually, I'll use orange. That's going to be 32 because 8 times 4 is 32 all over 3. I can just get that in here. Minus, that's going to be 32 all over 5. And we'll subtract here. That's going to be a -8. So that's going to be a -32 all over 3. And that's going to be a -32. That's going to be plus 32 all over 5. Or I'm really looking at 32 over 3 minus a -32 over 3. So I'm looking at, let me use this color, this one minus this one. Again, you can just put it in your calculator. But again, this is really going to be a positive 64 all over 3 because you're doing a 32 over 3 minus a -32 over 3. And then this one right here is a -32 over 5 minus a 32 over 5. And we have here, that will be a minus 64 all over 5. And if I evaluate that, that's going to be 128 all over 15. I did not do that in my head. I just did that in my calculator. Okay, so we are evaluated 128 over 15. So what is that? That is the area between the two curves, y equals x to the fourth minus 2x squared and 2x squared. You can also think about it as just the integral of what I've boxed right here of your integral of 4x squared minus x to the fourth with a lower limit of -2 and an upper limit of 2. Again, a derivative and your understanding of the tangent problem is very similar or kind of identical in a different circumstance as the area problem is to our understanding of integrals. Okay, so go ahead, check your learning plan for your homework, and I hope you guys all have a wonderful day. Bye, everybody.